So very pleasure to introduce Zhenghan Wang, and by way of introduction, so he received his PhD in 1993 at UC San Diego under Mike Friedman, who's a user analyst, and he started working in topology, four-dimensional, for snark theory, and so forth. Held a position in Michigan, and then worked through the ranks at Indiana University, and after a few years became more interested in data analysis, started working with Microsoft Research, and then in 2005 transferred to Microsoft Quantum Research, or Station Q, and there he started as a senior principal researcher, and has been working there on things connected to data analysis, together with mathematicians, computer scientists, physicists, engineers, things connected to this. We also have a five-year position at UC Santa Barbara, engaged there, and there's also a distinguished visiting research chair at the Theorem Institute, and lots of students doing research papers to his credit. And so it's a pleasure to here. I think about 4 times now, or at least. And he's going to teach us today about the mathematics behind topological quantum computing.
Excellent. So I think the reason the light on is those information. So I think probably I will turn off the light because it's better to read without the light.
Yeah, and anybody who's interested in dinner or 15 short one, please let me know right after the talk.
Yeah. 6:15, not 4:15.
What did I say?
4:15. I don't think the dinner starts now. Thanks, Thomas. So indeed, it's a great pleasure to be back again. I think, if I remember correctly, the first time I came here is 2003. I think I also gave the talk in the same room, actually. So this time it's slightly different, which is you hired many incredible, good young mathematicians and physicists, which work very close to what I'm talking about. So it's definitely much more fun to see the young people here. So I think I will start with my job to advertise a little bit about Microsoft. So this is a corporate thing. So Microsoft, among many others, is spending serious money to build a quantum computer. So I think actually we do probably everything you can imagine related to quantum computing, from software to all the way to hardware. And I'm really, although I'm a mathematician by training, I'm really closely related to hardware rather than software. So as I'm going to focus today is on, rather than the hardware, I will really talk about the mathematics. And so there are certain things I'm not supposed to say. So for example, you can ask me, do you have a quantum computer? I'm not supposed to tell you. It's a corporate secret. So I think this is a very interesting way to say it. We do have a program. I think it's going well, but I cannot tell you we have a quantum computer or not. So so let me say a few words about Station Q. So as Thomas mentioned, so I was one of the very early one, the starting from Microsoft Station Q. It's a theory group on the campus of UC Santa Barbara. And it started with Michael Friedman, my advisor. And after 2005, I think the last 2 or 3 years, we expand beyond theory. So now we have experimental people. So there's a group in Copenhagen led by Charlie Marcus. And there's the whole Station Q used to be the director is Michael Friedman, but now he's semi-retired. So Chetan Nayak is the overall Station Q director. And Chetan is a theoretical physicist, he's a professor at UCLA, and his advisor is Frank Wilczek. at MIT. So, and then we have theory at Santa Barbara and experiment at Copenhagen led by Charlie Marcus. Also the Delft, which is led by Leo Cohen-Haven. And then at Purdue, actually it's Michael Manford. Sydney is David Riley. So those are all experiments. Actually, it's kind of funny that at Purdue, Michael Manford is not from Microsoft. So actually I manage both Santa Barbara and Purdue. So I have actually MBE people report to me actually. So I do know some material science. So, and then we have computer science at Redmond led by Krista Schwarry. So that's the whole group in the world, about more than 100 people. So that's the whole effort. So the goal is to build this quantum computer. So, and I don't know, when I came here 10 years ago, probably like every 6 months, you see an article on quantum computing. And now I don't even keep track of any, like every day there's something on quantum computing. So probably you have read, there are many, many reasons, people want to build a quantum computer. But actually for me, there's one fundamental reason actually why, we really want a quantum computer. So of course, the government is interested because of, breaking code. Many people are interested because, now the significant money goes to the subject. But for me, the most important thing is this is a truly a new kind of fundamental scientific instrument. The way I want to look at it is that, this is kind of like the analog of a telescope or microscope. So when we have a telescope, we really can look really far away, and we have a microscope, we look really small. And a quantum computer is basically the instrument for us to look at the quantum world. This is the world which we have no idea. There's all those quantum weirdness. I think the main point is that we humans are more or less classic. We just don't have experience with what is the quantum world. I think the best application of a quantum computer would be just for us to understand, what's going on. We need to develop some kind of experience and feelings. And that's basically actually more or less the original idea for Feynman, which is a quantum computer is a quantum simulator. This is, I think, to me, that's the most kind of single important reason we really want this guy to have it. So, so I think that's really what I think justified why we want to build a quantum computer. And then you ask why topology. The main reason we cannot build a quantum computer is because of errors. And like I explained a little bit in lunch to graduate students, the main problem is that the quantum computer is kind of a contradiction. And you want to isolate the quantum system as isolated as possible because that will be quantum mechanics. On the other hand, that's called a qubit. And then you want to build 2 qubits. We want them to be coupled each other. And then you want the interaction. So it's a contradiction of isolation and the interaction. And the precision is just so difficult to control. There's all kinds of errors. So the idea of topology is the following. So I think there's probably some different.
Not bad, you?
Doing good.
It's more or less
Right on, man. Jealous.
same thing as something we know, kind of my favorite
I don't blame you.
math, which is the Gauss-Bonnet theorem, which is there's some number called the Euler Characteristic, topological invariant, and it's discrete. On the other hand, this information of Euler characteristic is spread into geometry because the integral of the curvature. And the curvature is a local thing. You can manipulate any way you want locally, but globally, you have no choice. The number is fixed. And that's basically the idea of topological quantum computing, which is you want to spread information into a global property like Euler characteristic. And then that cannot be destroyed locally. If you just bend the surface, the curvature, the Euler characteristic won't respond to you. It's just, that's basically what it is. So I can make it more precise later, but that's basically the idea of topological quantum computation, which is you want to protect your information by spread out. Actually, I like the, I have children, so I read Harry Potter. That's like Lord Voldemort. The idea to spread yourself into 7 parts, so you cannot be destroyed. And it's more or less the same idea. So this idea came from a mathematician and a physicist Michael Friedman, which is my advisor actually, and Kitaev, which is a genius. It's a very famous genius in. Anyway, so they basically kind of have the original idea of this whole idea of topological protection, and you can make it into a real mathematical theorem, which is what we are focused on for the rest of the time, which is the topological phase of matter. So just quickly, what it is that if you have a quantum system, and then you have the ground state, the excited state, and etc. And in a topological phase of matter, the ground state is well separated with excited state. There's a gap, spectral gap. And you can prove mathematically the ground state will be formed something called error correction code. It's a quantum error correction code. So therefore, in the ideal situation, it is information encoded in the ground state is completely protected, as long as you keep your system below the threshold, the energy gap. So, so basically, what we are, you can ask, that's, a question. Well, first I want to say, we don't have a topological qubit. And you might say, okay, you are way behind, but that's not quite true. Actually, we are not behind at all. So if you read newspaper, I think the number 59 becomes 72. So there are two ways to build a quantum computer. And at Microsoft, we go directly to this step, which is the logical qubit, or you can say the fault tolerant qubit. And most people, actually everything else, Google, IBM, and other places, they need to do two steps. They first build something called a physical qubit, which is the one which really amenable to local errors, like electron spin, photon polarization, diamond centers. They all very amenable to local errors. And they need to build those, like the number right now is 72, and maybe 200 pretty soon. And then they need to build those things so precise, they have to achieve a fidelity like a 99.999, probably 69. And then they go to the next step, which is error correction. And that's the called logical qubits. And that's the one you want to build your real quantum computer on. So therefore, the first step, right, everybody else right now is on the first step, which is the physical qubit. So that's the number you hear. They don't have any logical qubit. We don't have either. So we are more or less the same stage. And you can argue, who has, better one. I'm not so sure. Actually, Steve German, I don't know, there are physicists here, he tried to argue that he has almost a 1. It's not clear, but I think that's the closest, which is at Yale, they are close, the delta is very close to 1. And, but more or less, this state we are the same, which is we just don't have a logical qubit yet. So I won't focus on quantum computing too much, actually. I have the monograph, and I also have a AMS survey article. So, because I really want to focus on today is the what I'm really be doing, which is the topological phase of matter. So, so basically, I think Thomas mentioned I have two jobs. I have a job at Microsoft. I will need to build a quantum computer, but I also am a mathematician. So I want to do math. So the thing I want to do is really to classify topological phase of matter. And I think that's a very interesting mathematical question. So there are, actually, if you ask, the question of classify topological phase of matter, I think that's actually a question which is really too difficult right now. Actually, I don't think we even have a mathematical definition of topological phase of matter. So that's already an interesting question. So I really think, if you want to classify all so-called symmetry enriched topological phase of matter, that's probably too hard. But we know what to do in math. We have something too hard, you just make, special cases until you get something interesting and non-trivial. So the two cases you want to make is there's a combination of two things, symmetry and the topological order. And you want to make either of them trivial and then try to do the other one. So if you make topological order trivial, only care about symmetry, and that's something already very interesting. Okay, lots of physicists are doing this. This is called the SPT, symmetry protected topological order. And the famous example are topological insulator and topological superconductors. So that's actually very interesting already. But mathematically, it's more interesting to make the symmetry trivial. and just think about topological order. Then you can ask, what are they? And in one spatial dimension, topological order is called trivial. There's nothing interesting. And anything 3 and higher, we just really don't know. And the case we really know very well is 2 + 1 dimension. So that's actually our focus on, which is the 2 + 1 dimension topological order. And that's actually also what we do at Microsoft to use this to build a quantum computer. So that's what I'm going to fix on. And so just to say that, this 2 dimension, I use 2D means 2 + 1. So this is the spatial dimension, and that's a time dimension. This is not just, a purely theory, and actually this is really, really real. And the most famous example is quantum Hall state. And this is actually, this is a realistic, rendering of the material. So what you have is, you have gallium arsenide, some semiconductor both on top and the bottom. And then this is actually Hall-Stommer. He got a Nobel Prize for this thing, which is he can design the material so well that electrons at the top layer want to go to the bottom layer because of some potential difference. And then the design is so precise when the electron get to the middle, the potential difference disappears. So the electron suspended at the middle of the thing. Okay. And then if you as a theorist, you can just forget the top and the bottom. You can just imagine you have a pure electron sheet, gas of electrons. And then what you need to do next is you put a magnetic field perpendicular. And another ingredient is you want the temperature really low. And it's basically you need to be millikelvin. Actually, ideally it would be 4 millikelvin or 10 millikelvin. And the magnetic field would be huge. It's like a 30 Tesla. The world record is 45. So that's how extreme you have to be. Really low and really, really strong magnetic field. Actually, my children ask me sometimes, like, what are you doing? I said, oh, I just torture electrons. So that's pretty much true. You have a bunch of electrons, it makes it really cold. Then you have this magnetic field perpendicular. And that has a Lorentzian force. You have to travel in circles. Actually, that's localized though. So in this extreme case, they have to collaborate with each other. And then they form this beautiful quantum Hall state. So that's actually what it is, the quantum Hall state. And there are quite a few Nobel Prize for this already. And I think that Microsoft will kind of expecting another one with not being any unconfirmed. So I want to say one thing about this, about mathematics. So the integer quantum Hall discovered by Wang, which was an accident, like most of the important physical discovery kind of by accident. So he was looking for Wigner crystal. And he didn't discover crystal, instead he discovered quantum Hall. And he discovered this is, it's really a very simple thing. It's a piece of, electron quantum Hall simple. You do this, and then you measure, like I didn't have it, but this is a really interesting thing. So you have a sheet of electron gas, and you run a current this way, and then you measure the potential around this way. That's called a Hall conductance or Hall resistance. This number VH is something, there's a physicist in the audience, I don't know if it's E squared over H or H squared over E, one of the two. So this is electron charge, and this is a Planck constant. And then the whole either resistance or conductance is some number multiplied by this. And it's to the precision of 10 to the negative 10. So that's how precise it is. And if you think about the system, it's very dirty. There are all kinds of variations, but this number is very precise. It's like 10 to the negative 10. And then physicists start to wonder, how can it be so precise? And this guy come up with explanation, and it has to be topology, just like I said, the Euler characteristic. You said here is not the Euler characteristic, it's the first term number. So what happens is the following. If you think about this square as periodical boundary condition, and then you think about so-called periodic boundary, that's a torus. And if you go to the momentum torus, At each point, the momentum actually is a Hamiltonian, momentum dependent. And the Hamiltonian has a ground state, is one-dimensional. So therefore, imagine your torus has a line bundle, all this torus. And a complex line bundle has a Chern number. And this whole resistance or conductor is basically the Chern number. And that's actually the Nobel Prize for those TK and N formula. It's just this, what you measured in the lab is the first Chern number. And that's why it's so precise. So, and then there's other discoveries. So basically, what I'm interested in is that how do we model those kind of materials mathematically? And then try to classify them. And then really we want to do is to use them to build a quantum computer. So that's I'm going to explain what is this mathematical theory. By the way, so please ask any question, on your math, because, I know I will talk a lot of different things. So very few people kind of, really know, there's math, there's physics in there. So if you have any questions, so if you ask, I should say, this quantum Hall state is theoretically just, a sheet of electron gas. You have a magnetic field, and then you have a temperature. And it turns out the most important number to characterize quantum Hall state is that how many electrons in your system. So there's a number of electrons. And then you have a perpendicular magnetic field, and the strength of the magnetic field is given by how many flux quanta. And you can take the ratio. And this ratio is called the filling fraction, which is an important number. And actually, I have a good friend, Wei Pan. He's kind of the world expert of discover most of the quantum Hall state. I asked him, what's the numbers people have observed in the lab? So that's pretty much all of them. There are about 100 of them. So each of this number, in principle, represent at least one topological phase of matter. And physicists, normally is very good at, Cook-up theory. When this first started, those numbers are not discovered yet. They quickly come up with a theory to say, okay, you want to discover a quantum Hall state, this ratio has to have an all denominator. Look at them, 1/3, 1/5. And then, I think in 1987, 5/2 was discovered. The theory now is wrong. So it can't be even. So that became a long mystery of what is the theory for this 5/2. And all these odd ones actually has a very good explanation using Chern-Simon theory. So basically, each of these filling fraction has at least one quantum Hall state, and it can be mapped onto some Chern-Simon theory. And then 5/2, it turns out it's also kind of some quantum Hall theory, but it's a very different one. So that's actually basically, and there's a 7/2, which is basically the 7/5/2. They call particle Hall view. And this 19/8 is pretty new. I think people believe that's also a billion too. So that's basically all of them. So basically the mathematical question now become, how do we model those things? And if they really are what we think, then we should be able to use them to build a quantum computer. So there are two ways to characterize topological phase of matter. And the first way, use something called anyons. So I will explain both. And the second way is you concentrate on degeneracy. So let me start with the anyons. So you have a quantum system. And ideally, you have a pure sheet of electron gas. And it's just electrons, they have the same charge density. But there's nothing as perfect in real world. So they will have defects. You will have this, you want this to be pure, but you will get defects. It is quantum Hall state. And this defect behave like particles. So which means that they basically has a wave function like a Gaussian. It's really focused on this point. If they are particles, and then you can imagine to drag them around to do the so-called braiding. And in 2 dimensions, you can do braiding. That's not the same, you have 2 ways to braid things. So those particles, turns out, have a statistic which is not boson, not fermion. And I didn't draw the picture, but so what you can imagine is the following. So if you pick the right quantum Hall state, you have 2 of them. If you braid them, and then what you get is a phase in front of the wave function. And then we know for boson should be +1, for fermion should be -1. And for this so-called anion, it's invented by Frank Wilczek. And you can see the game is any on. So that means you can get any phase e pi r theta. But there's an argument you cannot have irrational multiple of pi because it's unstable. So it's really irrational. So it's e pi I, and then a rational number, like a 1/3. And you cannot get, I think the theory is if you become 1 over 100, that's not a quantum Hall state. That's actually become a Wigner crystal. So there's some energy computation. So that's actually, it's anyons. And the experiment is pretty good too, actually. That's the reason they got a Nobel Prize. Actually, the charge of this thing is not a multiple of E. Actually, you would think that's a contradiction. It's not, actually, because this is not so-called fundamental particle. So this have charge E over 3. And this is actually experimentally verified. And that's actually one reason they give out the Nobel Prize. So what they can do is you can cook up this kind of sample, and you can do a so-called short noise experiment, which is you can line up those things, and then you drive them to shoot on a screen. And then you can hear the screen, how loud it is. And this loudness has a slope, and the slope gives you this charge, 1/3. And I didn't draw the picture, but there's this clear experiment to tell you this is 1/3. And the statistics is a little bit of a theory. There's no direct, it's very complicated to measure it. But I don't think there's much controversy here that for like 1/3, you get a billion anyons. And what we are interested is one step beyond, which is the following. So in common situation, we have a sample like this. If you have an electron gas, and then you have, say, 4 defects, which are anyons. And then you can ask, what's the ground state? And in most situations, this will be 1. There's only 1 ground state. But in some cases, which we believe in 5-half, you can have more than 1 ground state. So if you have a more than 1 ground state, you can imagine the following. Suppose you have, say, psi1, psi2, and psi k. They are the basis of your ground state. The ground state is always a Hilbert space. And then if you take 2 particles and you do this braiding, suppose you start with psi1. If you have only 1 ground state, when you come back, has to be a multiple of this psi1. But now if you have multiple, and it will come back to the linear combination by quantum mechanics. And if you think about this, therefore, this motion of take core part, to pull 2 anyons and you braid them, instead of getting a single number, you get a matrix. So therefore, the statistic of those become a matrix instead of a number. And that's called non-billion anyon because we know for matrix which is bigger than 1, it don't necessarily commute. So non-billion just means what we call non-billion group. So that's what it is. And you can see that the important thing is the degeneracy, which is you have a quantum system that has more than 1 ground state. And that's the most important thing for non-billion statistics. So, so that's called ground state degeneracy. And that's very rare. And actually, Michael Friedman, my advisor, wrote a paper. He was so frustrated by why we couldn't just get those things. And he says the nature of the whole degeneracy is something very difficult to maintain because nature always wants to split them. That's not something. So if you want the degeneracy, at the moment, I think probably there are only 2 ways to get it. One is by symmetry, and that will protect some degeneracy, or by topological reason. And that's part of the 2 reasons, and that's what it is. So that's how you get degeneracy. And it's very, basically, it's the difficulty to maintain degeneracy, which makes it very hard to build a topological quantum computer. And that's what it really is. So I think I tell you so is it an hour or 15 minutes? An hour, okay. I think I have plenty of time. So I told you the quantum Hall state. That's actually Microsoft spent, I think, more than 5 years to work on experimentally. And then eventually discover we just couldn't control them well enough to build a quantum computer. So, oh, sorry. And then we, I think like 6 or 7 years ago, we switched gears. We changed to another way to do it, which is called the Majorana zero mode. And this is an incredible story of Majorana. So first, Fermi, which is a legend, believe his is as good as Newton and Galileo. But the more interesting story was he just disappeared. And but I think more important is that he did something really incredible in the following sense. So the beginning of this whole thing was, if you know that Dirac's famous equation, one thing which is really strange is he used complex numbers. And you can ask a philosophical question, why do we need complex numbers? Can we write down something with real numbers? And that's exactly Majorana accomplished. He wrote down the analog of Dirac equation in the real field rather than complex. And then has a serious consequence, which is if you write out the Dirac equation using only real numbers, and they will be self-conjugate. We have a self-conjugate operator. That means creation equal annihilation. So you have something both create and annihilate. And that seems so strange. And Majorana actually speculated neutrino would be some of these particles. But I think that story is still not clear. And then quantum metaphysicists start to think about, actually, this is I mentioned the name already, it's Alexei Kitaev, so he's a genius. So the story actually started a little bit earlier for Nick Reed, but let me start with Kitaev. So Kitaev was at Microsoft that time. So he wrote down a so-called toy model. He wrote down a Hamiltonian, and he made an assumption. And he said in the paper, this is completely unrealistic. Let me assume we can have electrons, no spin. And then I can write down Hamiltonian. I can realize non-binary anyons, not quite anyon, but a version of that at a nanowire at the two ends. But in order for this to happen, it needs electrons with no spin. And that's just impossible. But then topological insulator was discovered. And then Charlie Kane and Fulian, and they have different versions. And eventually came down to my colleague, Roman Luchin. And they said, it's true, you would never discover electron with no spin, but you can cook up a system. The electron spin is coupled with motion because spin orbit coupling. And therefore, you can really freeze out this electron spin. You can select a single spin. And that's effectively an electron with no spin. And that's actually basically what it is. So this Majorana wire. And what is really happens is that you have a semiconductor wire coated with aluminum, and then you have a magnetic field, and then you cool down with low temperature. And then there's something called proximity effect. The aluminum is superconducting and make the semiconductor also superconducting at the interface. And then the electron parity and even and odd have the same energy. And basically, literally a single electron at two ends locally. So that's what it is. And that's basically a realization of non-binary anyon. And that's what we are working on right now, the Microsoft project to build a quantum computer using this. So that's basically the latest. I wouldn't say we have it, but the evidence is really strong that we have this version of non-binary anyon. Okay, so now we'll a little bit more mathematical in the last 20 minutes to tell you about this whole theory about two-dimensional topological fields of matter. So I tell you about this so-called non-binary anyons. And now I want to tell you another way to characterize topological fields of matter, which is using the ground state degeneracy. So first I want to just flash the slide of what is a topological quantum field theory. And this is a definition due to Atiyah based on the work of Graham Siegel conformal field theory. So the way you imagine, I will give you the physical explanation, and the axiom is not that important, but the way it should be is the following. So if you imagine you have a theory, which is topological, and normally when physicists think about the theory, they always think, oh, the theory is in the plane, but now let's imagine you can put your theory on any space manifold. So I talk about 2 + 1. So therefore, you imagine your theory is on any two-dimensional manifold. So let's call this, manifold Y. And your theory is on Y, and then it's a quantum theory. So there's a Hilbert space, and there's a Hamiltonian. And the Hamiltonian basically like a scale to weight things. And the Hamiltonian will decompose your Hilbert space into eigenspace. And the one with the smallest eigenvalue, that's called the ground state, and then have excited states. And in the so-called topological physics, you don't care about excited states. Actually, you really care only the so-called ground state and the first excited one. And the first excited one will give you the anyons. And you may forget about the anyon, just look at the ground state. So therefore, for each surface, you will get a ground state, which is just some Hilbert space. And now you have a map from a two-dimensional surface to a Hilbert space. And this map, if it is a so-called topological quantum field theory, that would say your theory is topological. Okay. So a topological theory basically says the map from the surface to the ground state form a topological quantum field theory. So that's another way to define a topological physical matter. And this is basically a reformulation of what I said. And then there are really strong physical evidence this works. Actually, when I started this, there is conjecture due to Nick Reed and Razai, which is the 5½ is corresponding to SU2 level 2. There's a little bit of subtlety there, but more or less, the nonlinear statistical 5½ corresponding to this Chern-Simon theory SU2 level 2. There's a numerical simulation and there are experimental data. It's really a strong case. This is probably correct. So that's a second way to characterize a topological physical matter. Basically, you have a trade-off. You can either think about a topological physical matter and then think about excitation in the plane, and then they will have a braiding and the fusion and have all kind of properties particles. And that forms some algebraic structure called modular tensor category, which I will talk about. Or you should forget about excitation. You only look at the ground state. But now you cannot just think about the plane. You have to think about all spaces. And that's given a topological quantum field theory. And it's a theorem that those two things are the same. This is a theorem due to Trief, actually. A modular tensor category is more or less the same as a 2+1 TFT. There's a bit of subtlety I'm hiding, but that's more or less true. So that's basically the way I want to model this thing. So this is basically a summary of this thing, which is if you want to consider anyons, there's something called modular tensor category. And if you want to consider TQFT, that's three things more or less the same. If you need 2+1 dimension. So basically, we want to build a topological quantum computer would be to discover topological quantum field theory in nature. In the sense, we can really realize it. So with that said, now I will go to math. And you can look at this diagram to see that I put modular tensor category in the center. But that's kind of the central theme of all those things. That's kind of the most important, and kind of my favorite subject. So basically now, we have a mathematical problem, which is if you can convince yourself, those are the mathematical models of topological physical matter, and then you can go to the next step as a mathematician, which is just to classify them. Actually, that's almost by definition what a mathematician do, which is, you find some interesting structure and you try to classify them. So that's basically what I'm interested in. And it turns out in 2 dimensions, the modular tensor category is more or less, it's a very good analog, a generalization of groups, finite groups. So that's basically the analog I want to push, which is NER models, which is defined in unitary modular tensor category. This is just an extension of a finite group theory. It's kind of like quantum group theory. Unfortunately, quantum group has a different meaning. But here, actually, I think you can really think of quantum, a modular tensor category as a quantum finite group in the following sense. So there are 2 important features of quantum mechanics. One is superposition, and the other is entanglement. And the modular tensor category basically is the generalization of group theory using superposition. So group theory, you have a set, you take 2 elements, when you multiply, you get an element back, and then there's some axioms. And in a modular tensor category, you take 2 objects, you multiply, and now because it's quantum mechanics, you don't necessarily get one thing back. You can get a few of them back, and then they have a superposition, so you can sum them. So you have A tends to B, equal, instead of a single thing, you direct sum them together with a probability. And that's basically the first important structure of a modular tensor category. So it's really like a quantum group in the sense of you can have superposition in the multiplication. And if you think about this way, actually I already talked about this slides, which is you model a topological physical matter by think about either the so-called excited state or think about the ground state. And I don't believe there's a rigorous mathematical definition of topological physical matter, although it's very close. And if you're interested, I can talk about there are lots of subtleties as to why I don't think there's a mathematical definition yet. But I think I will skip those two. So, so now I think I want to talk about this so-called anyons purely mathematically. So anyon models for me means a unitary modular tensor category. And this is very common in many places, in quantum group, in vertex operator algebra, phenomenal algebra. That's why Dave and Corey interested. And it's basically the central notion in all those subjects. And I kind of consider this as a, kind of a quantum version of symmetry. It's kind of like a generalization of group symmetry in the quantum setup. And there's a very interesting reconstruction thing about modular tensor category, which is related to vertex operator algebra. We'll mention this because this is something I'm interested a lot, which is the following. So if you think about real samples, the quantum Hall state always has a boundary. And you can ask the question, the interior is a topological physical matter, and that would be a modular tensor category. And what happened to the boundary? And it's a well-known physical kind of a thing that in the quantum Hall state, the boundary is a conformal field theory. Okay, it's a chiral conformal field theory. And I actually want to extend a little bit further. I believe that is always true. If you have a topological physical matter, and the boundary would be always has one, which is a conformal field which is compatible. And this is basically a generalization of something. There are two analogs. One is called the Topological reconstruction, and the other is called the Deligne theorem, which is the following. If you give me a finite group, and you can study the representation category, which is a symmetric tensor category. And you can ask, suppose I give you a symmetric tensor category, can you reconstruct the group? And the answer is almost yes. There's only a little bit of ambiguity of a center. So that's basically the kind of relation between topological physical matter in the bulk and in the boundary. So basically the bulk has less information than the boundary is the representation theory of the boundary. So, so that's actually basically, the mathematical way to think about it. Actually, I don't think I will carefully define, but just quickly, as I'm talking about this word, a unitary modular tensor category is a categorification of really, a ring, and then with the commutativity, it's really a commutative ring, but the commutativity is replaced by braiding instead of order 2, can be any order. And there's some important notions I want to mention is that if you think about a group, and we have the order of the group, which is the number of elements. If you think about a modular tensor category, there's a notion called a rank, which is you think of topological physical matter as its own universe. And its own universe has particles. And you can ask how many different particle types. And that's called a rank. And in terms of representation theory, it means that you give me any algebraic structure, and you ask how many irreducible representations. And that's called a rank. And it turns out the rank is the same thing as if you think about topological quantum field theory, you assign the torus a Hilbert space that dimensions the same thing as the rank. So that's basically this way to define it. And then there's another, I think the examples, there are lots of them I really won't go through. I think the most famous is the come from quantum group, which is related to Chern-Simons theory. There's a kind of a conjecture that by Wheaton to Greg Moore, that everything is related to quantum group. So it's more like there's nothing really new. I'm not so sure it's true or not, but that's a conjecture. So there's something related to finite group, and then there's this quantum group, and it's conjectured to be all. So now let me just tell you a few theorems which I want to put this analog. So the first theorem I want to mention is this beautiful theorem of E. Landau. For the physics here, this is not your Landau. This is not the physicist. This is actually, he was at the Göttingen, which is a number theorist. So he had this very elementary theorem, which is if you fix the number of irreducible representations, and then there are only finite many groups with that number. So that's actually a pretty nice. Actually, it's not completely elementary actually. So that's his theorem. So I made a conjecture back in 2003, which is there's a version of this theorem for modular tensor category, which is if you fix the rank, then there are only finite many modular tensor categories. So it turns out this is actually true, which is not surprising. It's basically, a very elementary thing, except the proof is really different. It's basically here the proof using the class equation over integers. Here I kind of need to do some kind of a class equation over complex numbers, but that's too hard. So I have to do some number theory. So it turns out we use a very deep analytic number theorem, which has to do with S units. So that turns out to be true. So there's a version. And then I want to see another theorem, which is if you think about mathematical object you want to classify, and the way we want to do is always want to say, oh, we want to discover some invariance. We associate some invariance to this object, and then we will just classify using this invariance. If you have a modular tensor category, and then the two most important invariants that's called modular data is the following. It's easier to define with the topology. So if you remember, I had a theorem that says a modular tensor category is the same thing as a topological quantum field theory. So what a topological quantum field theory does is you associate a Hilbert space to a surface. But there's also a three-dimensional version, which is you associate invariants to links and knots. So if you have one, if you believe this statement, and then you can ask the following. So if you have a topological quantum field theory, you can associate the invariant to any links. And the simplest link is the N knot. And then you can color this N knot by a simple object, or an anion. So this is a physical interpretation. You imagine you start with a vacuum, and then you create a pair of anions, and then you annihilate. And this process has a quantum amplitude. And this environment is just that amplitude. And that turns out to be a very important number for the modular tensor called the quantum dimension. And there's another number, which is that the environment is so-called frame length. So instead of you create a pair of a particle like this, what you can do is the following. You can imagine the physical process that you start with a vacuum, you create a pair of a particle, you create another pair of a particle, and then you bring the middle two, and then you annihilate, and then you annihilate. And that has an amplitude. And then you divide it by the quantum dimension, which is the amplitude for this process, to get a number. And that number turns out is always norm 1, but more important is a root of unity. And that's a theorem due to Waffa. It's a relatively deep theorem. So, so that's actually another number. It's called a topological twist. And this is basically encode that the spin of that anion. And then for each modular category, you can form this number, which is take the quantum dimension square and add them up. And it's well known now called D square, and that's encoded something called topological entanglement entropy. So this D square is the analog of the order of the group. So this is basically, if you ask, what's the analog of the order of a group, and that's this number D squared. In general, it's a complex number. So now I want to define another matrix, which is invariant, which is the Hopf link. So you can imagine either as an invariant for the Hopf link, or you can do, just as I said, the physical process, create a pair of particle, create a pair of particle. Now instead of braiding once, you braid twice, and then you ask the amplitude of this process. And that's this number called SAB. And you can form two matrices. And the magic thing is these two matrices form a repetition of SL2Z. And for mathematicians, when you see SL2Z, you immediately think about number theory. And that's actually true. So this has a lot to do with modular form. Actually, it's a vector valued modular form. And that's actually the connection to conformal field theory. The conformal field theory characters, they are basically generalization of a modular form. So that's what it is. So those are the most important invariant. And now I want to state another analog of a group theory. So in elementary group theory, there's a theory called Cauchy theorem, which is the following. If you give me a finite group, there are two numbers you can associate to it. One is the order of the group, which is the number of elements. And the other is the exponent of the group, which means the smallest integer, every element raised to that power will equal 1. So for example, if you take Z2 cross Z2, the order is 4, and the exponent is 2, because everything's order 2. So obviously, these two numbers are different. But if you think a little bit more, there's some common thing, which is if you take the order, you break into prime decomposition. If you take the exponent and you break in prime decomposition, the prime appeared in this exactly the same. Okay. So the order and the exponent, they are normally different, but the prime factors are exactly the same as set. And it turns out this has an analog in modular tensor category. As I told you, the order is kind of D squared, but there's another version, which is I explained the T matrix, that this T matrix, by Waffa's theorem, that theta A is a root of unity. So therefore, you can ask the order of the T matrix. So that's some integer. And then the dimension, that's also kind of some order. So actually, I have to say, sorry, this order of the T matrix corresponding to the exponent, and this dimension corresponding to the order of the group. And then, as I said in this Cauchy theorem, you break this into primes, they are the same, but these are not integers, so you cannot break them into prime. But there's a version you can do in the number field, and you break them into prime ideals, and it turns out they're also the same. So that's another generalization. So basically, I want to claim that there's a very good analog, almost all the elementary theorem from finite group theory to modular tensor category. So that's kind of justified. This modular tensor category is kind of like a quantum version of a finite groups. So I think I will basically stop here. Is that I think it's quantum computing. It's a great opportunity for mathematicians actually to think about quantum mechanics again. If you think about, actually I was at IPAM maybe 2 weeks ago, the whole conference kind of to get a understanding, to find a way for mathematicians to make a contribution to quantum computing, and you can imagine, all the things. So I kind of give an argument why mathematicians really, will be very important to this. If you think about information science, mathematicians extraordinary contributions. Classical computation start with, long time ago, actually it's Barbie, and he had this machine. Actually, he's a mathematician in winter. But then the next important figure is Alan Turing, and he's a mathematician. And the next one is a Shannon, which is basically a mathematician. And then there's a von Neumann, and that's another mathematician. So that's how big, mathematician role played in this classical computation age. And now quantum computing, I think, I'm pretty sure mathematicians will also play important roles. We already have two, well, at least, we have two mathematicians which are working, make fundamental contribution. We have Peter Shor, which discovered quantum, spectrum algorithm. And then there's Michael Friedman, which is, driving this whole topological quantum computing. Actually, for me, Peter Shor's contribution, more important than his factoring, actually is the error correction code. So actually, the history was, when he discovered Shor's algorithm, people say, okay, that's a beautiful theorem, but you will never be able to build a quantum computer because error correction just won't work. And actually, Peter Shor came back 2 years later, and independent Andrew Steen says, although you cannot just mimic, in a straightforward way of classical error correction, but you can make quantum error correction code. And that leads to this important theorem called Theorem theorem, or threshold theorem, says if you can build a physical qubit precise enough, in theory, you can build a universal quantum computer. I think that's actually more important. So I think this actually leads to a lot of things mathematicians can do, and actually related to what I'm going to talk about tomorrow, which is I will talk about quantum field theory. I just want to say one thing, which is you can ask, why it's so hard to build a quantum computer? Actually, it's kind of not too surprising, because the model of a quantum computer is built on quantum mechanics. But in reality, you have quantum field theory. So what you're really doing is you are simulate quantum mechanics using quantum field theory. So there's some mismatch here. So there's lots of errors here. So anyway, I think people are talking about second quantum revolution. But I think mathematicians, definitely has opportunity even, just to think about, mathematically what the quantum field theory will be. And that would be really an interesting question. And I can speculate more about this whole thing. And in particular, I've really found, I'm doing some research in that too, which is I truly believe, logic is not, something inherited. I think it's empirical. So there's a possibility if you have a quantum computer, your logic needs to be modified. And I don't think that's too speculative. So with that said, I think thanks for your attention. So this is just a fun Microsoft video. Excellent.
So you talk about the 2D topological phase of matter in the book. Typically, usually it has a boundary, right?
Yeah.
And you talk about gap-based boundary, which is usually a homological theory of parallel topological order. Can you say something about the non-parallel topological order? We can have
gap
boundaries. How much do we know about that?
I think we know a lot about gap to boundary. Actually, that's Dave. Those people do. So I think for those double theory, I think it's still a conjecture, but there's no doubt probably it's true, which is if you have a double topological order, and then the gap to boundary is one more corresponding to this modules, this module category. But the way I talk about this gapless boundary is that actually, even for those double theory, there are still compatible gapless boundaries. Here's an example. You take the toric code. It has gap-to boundaries, but it also has a gapless boundary because toric code is also realized by SO16 level 1. And that's a conformal field theory. So there is a compatible gap. What I want to claim is no exception. Doesn't matter it's chiral or non-chiral. Every topological order has a compatible gapless boundary, which is a conformal field theory.
And for the gapless boundary toric code, do you need symmetry to protect it?
No, you don't. The central charge is 8 rather than 0.
Just for toric code.
Yeah, for toric code.
Oh, you mean like EA, it's not a EA on top of toric code.
It's not quite, but you can realize that way.
I see.
It's actually the interesting one to not split. It's basically we know that the topological order only determines the central charge mod 8, and you have a choice of not 0. You can choose any 8. Now for the trivial one, you have the choice of a WAC, or you can also choose master.